Brought to you by My Green Egypt, green resources for efficient energy. Hello, and welcome to the first tutorial of this video series of a UPS that will be upgraded later on to a photovoltaic solar hybrid inverter that says it can work either as grid-tied or off the grid. A typical UPS is comprised of battery bank, battery charger, an inverter with a way to switch the load between grid power and inverter power in case of grid power failure. There are many types of UPS configurations pertaining to the load switching mechanism. The most prevalent nowadays is the line interactive and standby types, especially in small power ratings. Standby isn't the best option regarding load switching speed, but it is the simplest, so we'll start with it. Battery charger. The battery charger is responsible to charge up the UPS batteries and to keep them in that state as long as the device is connected to the power grid. The charger has to be able to control both output voltage and current in order to cope with the battery's requirements at each charging stage. There are two ways to achieve that voltage and current regulations, by either using linear or switch mode technique. Linear regulators are bulky, waste a lot of energy, and it can't handle high current outputs. Our design needs an output current of about 10 amps at 12 volts, so we'll stick with the switch mode technique. There are many switch mode schemes out there, but we'll choose the flyback configuration since it can provide us with the isolation needed for protection from the utility voltage, and at 100 watt max it proves to be the simplest and cost efficient since it doesn't need a filtering inductor at its output. As you can see here in the picture, this is the schematic of our battery charger inside our UPS. The software that I'm using now is the CAD software Eagle. This package is used to draw the schematic and also to design the PCB layout prior to sending it to a manufacturer to get a nicely done PCB. As we said earlier, that we are going to use a flyback configuration. The flyback configuration has in the middle a flyback transformer. The flyback transformer isn't basically a transformer because, as the name implies, a transformer is supposed to transform the power from its input side to its output side. But what the flyback transformer basically does, it stores energy during the conduction stage of its input and then it transforms it back to the output during its off state. The battery charger is basically a converter that can control its output voltage and output current. If the battery is fully depleted or the battery is deeply discharged, that means the battery is hungry to get all the energy it can get from the charger, and the charger in this stage will try to output its maximum amount of current, and the voltage on the battery's electrodes will rise gradually till it reaches a certain level. In a 12 volts battery, that value is 14.7 volts. If you are going to rise the output voltage beyond that level, the battery will start to overcharge and air bubbles will form inside the batteries. That means you will evaporate the water inside of it, and that means that the battery will lose a portion of its capacity. Continuing doing that, you will at the end destroy your battery. So you have in the second stage, which is absorption charge stage, you have to maintain the voltage at 14.7 volts for 12 volts batteries. At this stage, the current will start to fall gradually till the current reaches another value, and this value practically it is from 5 to 10% of the battery's capacity. If you have a 10 amp hour battery, that means 0.1 amps, you have to enter the next stage, which is the float charging stage. At this stage, you have to lower the output voltage from 14.7 to 13.8, and you will keep the batteries as long as they are connected to the charger. So basically, this is what our charger is going to do. Here we get to the inverter part of our UPS. The inverter device is responsible for converting the DC power from your battery bank into a usable AC power at its output. This AC power is similar to the one that you get from your receptacle on the wall. So what this design is basically as, it comprises of two push-pull transformers that are connected in parallel at the input and in series at the output. Both of these transformers are driven using two MOSFET transistors for each transformers that sum up to 4 transistors. Each 2 transistors are connected on its gate side to a bootstrap IC. As you see, this transistor Q4 is connected to transistor Q2 to the high side of this bootstrap IC. This bootstrap IC is the famous international rectifier 2113, and this bootstrap IC is driven using this small microcontroller. This microcontroller is the AT90 PWM3P. This microcontroller is being designed and manufactured from Atmel Corporation. It employs a good PWM module inside of it. It's called the power source controller. So this microcontroller will generate the sinusoidal PWM signal that will drive those transistors, and then this voltage, the sinusoidally modified PWM voltage, will be stepped up on these transformers, and then it will get rectified on this bridge. And this LC filter here will try to reconstruct the positive portion of your sinusoidal waveform, and then this positive portion of your sinusoidal waveform will then be converted into a complete sinusoidal waveform on an H bridge, which is not shown here. It will be added up later. So that is everything for now regarding this inverter design. We'll show you in the next video the experimental results on the oscilloscope once this design get manufactured and tested. So please stay tuned for the next video. And if you have forgotten to subscribe to our YouTube channel, please do it now. You press the subscribe button below, and don't you forget to like our Facebook page. Thank you for watching this video, and see you in the next one.